to close that and open it again.
It's going.
Is it ready?
Yep.
All right. All right, Joel, we are going to just talk about liner for a second. And I'm not sure how many notes you took during that hubbub while we were trying to get it out of our calculator. I just want you to recognize that liner is, L stands for linear, and you look at the data, and you're looking for a progression that is somewhat linear. So if there's complete scatter of the data, then you say no, we can't do this any further. All right, independence is like it was before, but then it got messed up after that, didn't it? Normal. Where do we look for normality? From your notes yesterday, Haley, what were we looking at to be normal? The residuals. The normal residuals. So that was a lot of bootstrap to get it out of our calculator. It involved L1, L2, L3, L4, and to some degree L5. So what did we end up looking at? Do you remember what kind of chart did we look at, Morgan, when we were doing to see if the residuals are normal?
Was it a histogram?
We did. All right, I didn't want to confuse you overly, but there is another choice in those six choices from your stat plot. I think this is a histogram. But you could also use this choice. And if you look at the picture, the thumbnail picture, it's just a straight line of dots, not even pretty straight. And I just wanted to remind you about that choice, and that's called the normal probability. We called it the normal probability chart. And do you remember us doing that? If it's straight, then you're dealing with normal data. Do you remember that?
Is that the one with like the stripe, or no?
No, it's not. Check the normal probability chart for straightness. So that's another way you can tell that data is normal. And we used to do that. So I just wanted to remind you about it. And let's look, and we might pull that up just to see if we can do that in a minute. We'll finish equal variance. I think, Morgan, what you said was right. I kind of looked it up. We had a equal variance. Would you remember, Morgan, what chart we were looking at for that?
The residual plot.
The residual plot.
Kevin, thank you.
Yes.
The residual plot actually took the X value here, and it had dots around it like this. And I was telling you, I didn't think that our backpack actually had a very good display for E. And Morgan said, well, I think the spread above was pretty much like the spread below. You need to go to the bathroom?
Yeah.
Yes. All right. So these are the spread above and the spread below is what you check. So
Like
no wonder all these years I've been, so you want the spread above to be similar to the spread below. And the thing you really don't want, as X gets larger, you don't want like a larger spread going on. So you don't want the spread to be going bigger like that.
You don't want any measurable shape.
Right. So you want just the equal scatter above as below. All right. So let's look for equal scatter above
You said what's the last name
and
of the school?
below.
It's better if they're more
Christian.
symmetrical-ish, or does that not
Wait,
matter?
wouldn't it be school?
We don't want cement. We don't care.
No,
about
like,
don't need-
oh,
we don't
okay, we
care.
don't care about it.
Shannon, did you say something?
Do you have my test?
I do, but can I get it in a bit?
Yes.
All right, remind me. All right, random is, the sample has to be chosen randomly or the experiment conducted in a random assignment of experimental variables. So let's go back here and see if we can get a normal probability chart out of our calculators just for a minute, and then we'll go on. So you are looking at stat plot. You already have the data still in. So we're trying to do this one the other way. I showed you how to do it with a histogram yesterday, and now we're going to do it with the normal probability chart. So go to stat plot, turn plot 1 on, I don't care, everything else off. We can do plot 1. And hit this selection here. It's your normal probability chart. What does it ask for?
Data list and data axes.
All right, so the axes I know is going to be the x-axis, and what's the other thing it
Data
asks?
list.
Data
Is this what it's
list.
supposed to look
Data
like?
list for normal probability, and we're looking for residuals. So if I remember, they were lurking in 4, right?
I think so.
All right, so we're going to do L4X. Is there any other question that I have to answer?
No.
Okay, then pull that up.
Data list L4.
All right, so see how straight Haley's is? That means the data, residual data is normal. See this one?
Oh, there.
This is what you're trying to get. You have your calculator?
Is it L4X?
I'm sorry?
No,
You're,
Brian,
you're,
stat
you're not on the stat plot. So,
Snap
Dan,
plot.
not doing yours?
Here, Adrian.
Sorry.
Good. All right, thank you. All right, so, alrighty, so, again, I kind of like that way because when I look at histograms, they just don't ever look normal to me. So I prefer this one, but I didn't want to put too much on you yesterday, so I prefer this. So did you find stat plot?
Yes, I did.
Okay, all right, now you're going to tell it L4
L4.
and X is your axis.
I have that. So then,
Enter.
and what's the Y list?
There's no Y list.
The last plot.
Plot 1 us for
All
Y
right,
list.
hit enter.
Andrew, no, doesn't Andrew.
Or hit graph.
Change it
I'm
to the
sorry.
last square. Like, you know how it's in like histogram,
Oh, I
dot
don't
plot.
And then what not us for
Do you
Y?
have data in your calculator?
I think so, yeah.
All right,
The
you
histogram one?
have data in
Histogram one?
L4?
Whatever the last one is.
Oh, wait, which one is it? Oh, it's the dot plot
All
one
right.
kind of.
All right, for those that were out of the room or not here yesterday, we'll figure it out
Yes,
later.
I have data in L4. Is the
All right,
data
everyone
axis
else?
X or Y?
Got it?
What about marks? Is that anything?
Let me
No.
give you a
That doesn't matter.
handout.
That's just what kind of dot you have.
Let me give you a handout that kind of summarizes Liner.
Is this what it looks like this time?
It is.
Now I have data.
Now, if it's linear, that means your residuals are normal.
It's so close to
Did you
spelling
show?
linear.
Did you show him? Okay. All right. All right. Let's read this fairly quickly. So I need one for Kevin and one for Dan. All right. Joel, not Dan. Dan, you can read for us. Read to me about linear, where it says conditions for regression.
Okay, and is that beta? Is that the
Yeah.
symbol?
Yeah.
The B? Okay. The actual relationship between x and y is linear. For any fixed value of x, the mean response is mu of y. Mu sub y
Right.
falls on the population. True. Regression line mu sub y equals alpha plus beta x. The slope beta and the intercept alpha are usually unknown
All
parameters.
right, so now he read it has to be linear. Now, we'll have Maddie, you tell him how you actually check. He's saying it has to be linear. Now, you're going to read below and tell how we can do that. Maddie?
Okay. So it says, examine the scatter plot to check that the overall pattern is roughly linear. Look for curved patterns in the residual plot.
Well,
Check
that's something we didn't do, so that's another way. So we could do the residual plot. It's an option. I prefer just to look at the data, but if you look at the residual plot, it should have equal scatter. Go ahead.
Check to see that the residual center on the residual equals 0 line at each x value in the residual plot.
Okay, so it gets complex when you use the residual plot. Just look at the data. If it looks linear, if it's flowing from low to high or from high to low in some linear amount, call it linear. All right, Andrew, read independent.
Individual observations are independent
All
of each
right,
other.
and so Andrew, also read how you do that at the bottom.
Okay. Look at how the data were produced. Random sampling and random assignment help ensure the independence of individual observations. If sampling is done without replacement, remember to check that the population is at least 10 times as large as the sample.
All right. Haley, would you read normal above and normal below?
Sure. For any fixed value of x, the response y varies according to a normal distribution. Make a stem plot, histogram, or normal probability plot of the residuals and check for a clear skewness or other major departures from normality.
All right, I recommend the one we just did, but it's your choice.
Above all, because then above the histogram, because yesterday it had that weird gap.
Yeah. I'm just never confident that my bars are collecting enough data in each one, you know, so this is, to me, is if it's straight enough, I'm gonna say. All right, Maggie, would you read equal variance above and below?
The standard deviation of y, call it standard deviation, is the same for all values of x. The common standard deviation is usually an unknown parameter.
All right, so how do we check for the equal variance? This is the bottom part is where you actually do it. The top part is the theory. Okay, so how do we look for equal variance, Maggie?
Look at the scatter of the residuals above and below the residual equals 0 line in the residual plot. The amount of scatter should be roughly the same from the smallest to the largest x value.
All right, so again, I think Morgan was trying to tell me that yesterday. When we did it, it looks sort of like that. And I said you had to look at each x and see if it was the same above and below. But the way this is worded is saying, is the scatter similar below and above? The thing that is you don't want is to have, say, this scatter, and then as x gets larger, the scatter gets larger. So it's sort of like coning out. I don't know how to say that.
It's like a circular scatter.
So the scatter is getting bigger. We don't want that. So we want an equal scatter. All right. Last one, random above and random below. Shannon, can you read that for us?
The data come from a well-designed random sample or randomized experiment. See if the data were produced by random
Same
sample
thing.
or randomized.
Okay. All right. Random is not that different from before. All right. So we're gonna are gonna do one of these, but I haven't taught you how to do one, and I have a little bit of theory before that. So if you would turn to the back of your sheet, the handout, the day 1, 2, 3, 4, 5. And if you turn up the back with the second page to the back of the first page, you'll see that graph like I started on the board.
Wait, are you talking about the back of the first page or the second? Looks like
Guys,
this.
flip your page once and that's it.
All right, so if I have an x, remember yesterday I took the normal old xy axis and I threw it on the floor. So now the x-axis from your perspective
Cubism,
looks
yeah.
like that.
Is it still 90 degrees or no?
It is,
I said
but
jinx,
so
and
yeah.
Oh, it's like a helicopter.
See that?
Oh, yeah, if it was like this.
What's this
now.
made of?
All right,
I said it first, right?
What's this made
But I
of?
said it for you, so there's no jinx.
No, you didn't say.
I started that graph for you.
What's this made of?
And I am going to ask you to put a couple additions onto it now. So let us see if you can do that. Hopefully you're working with pencil. All right, so here are x values. So I'm going to continue talking to you about this as if it is the backpack weights. And I started this yesterday, so you have a taste for it. All right. Let's take this line, and I don't think it's on your graph, and you can't draw it just yet. So I can, but you can't. You're going to add it in a few minutes. So this is the real McCoy regression line for the whole population. This is our MY. It's the big kahuna that we're looking for. Now you cannot draw that in yet because you don't know exactly where it goes. I will guide you, draw it in a minute. Now, x of 1 on mine, let's see.
I was thinking it was
Yours has an x of 1.
It's a fish or a
All right,
bear?
let's say that x of 1 is the backpack weight, the body weight of 103. So, that was one of the guys on our sample. He had or she had a 103-pound person. And in backpack, when we did the backpack example, actually, I don't have that data. Let me change that. Let's say we had 112. We could have used any data. Say we were looking at the person that's body weight was 112. So with our old formula from chapter 3, I should know these numbers by now. A was 16.3 and B is 0.0908. I got it?
Yep.
All right, so if I'm going to predict the weight of this person's backpack, I would go in and put in the 112. When I did that last night, I could predict with that a regression line of a person would carry almost a 28-pound backpack. So that backpack is not the whole story. That data is coming from one sample, but we know that when there are more than one person that weighs 112, and they won't always carry a 28-pound backpack. They will carry, some of them will carry more, and some will carry less. So it really, in the whole population, it turns out that 112 does not yield one number. It yields a whole normal display of numbers. So this value for X could have all these different values for Y. These will be the most common because they're around the mean. These are going to be least common, but they are possibilities. So there's going to be a range of values for backpacks that we weren't ready to accept earlier. So underneath this one, I don't know if I drew this for you, from the mean to that, can you draw a bar? Did I draw that for you?
No.
Okay.
Wait, well, we don't have the bar. You told us not to draw the bar yet.
It's on the back of the first page.
No, but it's
No, but you told us not to draw the NY
orange one.
equals. Yeah, we don't have the orange bar, so we can't.
Yeah, I
draw
know,
one.
and that has nothing
It's
to
gonna
do
go
Oh,
with
draw a
the
line and a
top.
dotted line. Okay, sorry.
Oh, we have the dotted line.
Yeah,
Yeah,
so
sorry.
draw it from the peak to
Is it
to that.
a straight up and down line? Or is it
Sort of,
okay?
yeah.
It's on the top of the.
Not supposed to be exact.
Look at that.
All right.
But you're looking
Now
at it.
let's
Roll it to the
say
top of the thing.
X say for every person that's 112 pounds, their backpack weight is not going to be 28. It's going to be a whole bunch of different ones. So some of them will be very light, some of them will be very heavy, and some of them will be near the mean.
Why are we doing this?
We should do.
How do I know whether
Next
to
time,
make the line
don't stop when you
slanted or
do
not?
What do you like?
For the stat, we should
just
print
make it
out
like
the
that.
picture of the person at the bottom of the
All right,
board.
so
Pretend
now
like it's a regular like pill.
let's put in another value for X. Instead of 112, what's another backpack weight? Someone got your backpack weights in front of you? What's there another guy greater than 112?
No.
He was the highest?
No, 112. I don't know what they are, guys.
Oh, it's not? Okay, give me somebody in your backpack. All right, it doesn't have to be.
Wait, was
116 is the closest.
What is it?
116.
All right, let's go up to 116.
wait?
Wait, how are you doing this
Backpack weight is L2, right?
L1.
Pardon?
Wait, no, we're going with body
Backpack weight is
Body
L2, right?
weight.
Where
Or
are you
body
guys-
weight.
X is body weight.
Where are
Well,
these
the
numbers
highest
equal
body
to
weight
now?
is 187.
Oh,
It's
Oh.
not talking about the highest.
All right, so I'm just giving an example. It doesn't matter what number we use. It
Is the
doesn't.
data
Let me pull up my,
The highest
No, it doesn't have to be. This is anybody in the whole world.
Which
all right?
L is-
So
which L
if I
is
put
this?
112, a person that weighs 112, before we said this would predict their backpack weight.
You
Did
should
we
do it
not?
on the inhale.
wait, where are you getting these numbers
I
from?
made it up out of my head.
112 and 116? Okay.
I think somebody told me 116 was on the list, but I
Yeah,
don't
yeah,
care.
it
The
is.
tone
I don't
right when you
care.
do the next
I don't
one.
care.
What's
Your
yeah.
L1.
Backpack
Your
was
L1.
just put
Okay.
calculated already.
I was confused.
So, Haley, could you
Yes.
put in for me 116 there and tell me
Melody
what
doesn't use
we predicted for 116?
Oh wait, I should already have that in the list, right?
Yeah.
I go to set, edit, and then, okay. Okay, I can do this. It should be in L3, right? No.
Yeah, I think it is.
Yes, 26.8.
All right, so according to our old method, when we put in a person that was 116 pounds, we got out
26.83.
26.83. Why didn't it go up?
Oh, L2, yeah, because L1 was 116, L2 was 28, and L3 was 28, 26.
All right, well, would you
Yields
check,
losses we
or
are,
would you
Joel.
check this calculation?
I did it, I
yes.
confirmed this
So, like, he- I guess he
26.83.
Yeah, I have 26.83 on mine.
All right, would you also do then 112? This must not be
The
right.
secret word is lollipop. If you come in and say
112 is
you
26.4.
Okay, that makes
special,
more
you get
sense.
a lollipop.
26? Okay. All right.
26.4.
All right, and so
If you say
then when we
anything
put
else,
in
you'll get that
116, Haley, what we get out?
26.83. So
All right,
first
so
one
it's a
was
little
26.
more. It was a little more. All right, so when we put in 116, we are expecting
Joel's.
a body weight, a backpack weight that is also normally distributed. Some people will carry the 26.4, but some people will carry a lot more than that, who weigh 116, and some will carry a lot less. And last, so let's just give that a mean.
It's not wood.
And last one, I'll just call it X3. It doesn't matter what it is. We're going to have the same thing happening. Instead of getting one value out for Y, we're going to get a whole spread of values, because that's what happens in a whole population. Let me move this down a little bit. All right. I put the mean in. All right. Interesting enough, now again, this is theory, and it doesn't really, you really won't need to understand the theory to do the confidence intervals, but I just want to give it a stab. All right, so, all right, what I want to say about that is, note, for each value of X, there is an observed response in Y that varies according to the normal distribution. That's all I really want to say. I'm actually going to write it down. Note, for each value,
Quick stab to the heart, sorry.
we'll call it X of I. So it could be any of these and many, many more, an infinite number more. For every value, X of I, there is an observed response value, Y, varying according to the normal curve.
Veil.
Is that really a thing?
The normal curve with mean. Now this is the part
Okay.
that
I was like,
I'm not sure if your graph can show it or not. Remember, every normal curve is described by its mean and its standard deviation. I can tell you two things, and everyone on the planet can give me the same normal curve if I give you the mean and the standard deviation. So I want to see if I can draw out of you what these two are. According to the normal curve with mean blank and standard deviation blank. All right. So what I want to say, if you could write that out so we can talk about it, then we can easily fill it in. It turns out that now
She means value,
you
Joel, not
can
veil.
draw in this curve, because this curve will intersect this point, and this point. So can you do that now? You can draw in that curve connecting those three orange dots. Not curve, it should be a straight line. Did yours turn out okay?
How do we
So,
know where to start it? Do we
Take-
start it at?
Well, if the three lines are
It's
three
easier to start at
three
the-
dots will determine a straight line, so it'll flow where it flows.
Like
It's
if you
easier
put
to
a ruler underneath.
Yeah,
It
right.
doesn't really.
It's easy to start at the farthest one and come back.
it's pretty straight.
They should line up.
Connect the dots, guys. Got this.
Good. All right, good. Yeah.
I wrote the equation.
How about yours? Good. All right, see how much easier to put in now than it was
Yep.
earlier? Okay. All right, good.
Think about
All right, so those three lines intersect at what point on each of the normal curves?
The mean.
The mean,
Yeah.
that's right. So the mean here, the mean of this curve is here, and the mean here, mine didn't show up so good. That's supposed to be at the mean, and the mean there. So that is noteworthy. So that is on the orange line, is it not?
Yeah.
So we're going to say that the mean is mu sub y. And the standard deviation, we can't be so specific. We just know that the standard deviation is the same. So let's say that the standard deviation is, put it in parentheses, that tells you it's not always going to be 3, but for our purposes, let's say it's 3. So I'm going to draw it in on each of these. Remember, the standard deviation is from the mean to that first change in curvature.
Right, where
So
it
this
turns
is
into a smiley.
3, this is 3,
Change in the
and this is 3.
How would we find the standard deviation?
Yeah, we'd have to just do a one variable statistics, yeah. So we're just talking a little bit in general theory
Will we
right now.
ever, will you ever have
It
to
doesn't
make
make
us find
sense
it?
for
Do you
them.
think?
No,
Like,
you might need the
using
standard
the other
deviation,
things that
but
we've learned. Like, I don't know when
not for
It's
this
like
graph.
learning,
Right.
it's like learning a bunch of different classes.
Alright,
Like, I have no idea how they
so now, again, I kind of reiterated this. Who put the 112 in their calculator and found it?
Me.
Alright, got the what number again?
26.46.
So, wait a minute. So, before, in chapter 3, we said a 112-pound person will definitely carry a backpack, predictable to be what?
26.4.
26.4. And we did that by putting it in that least squares regression line. But now, we are going to say that, let's say that that number was 20 what? 6.4?
Yeah, it's
It became a look that
So
constantly
notice
that I thought was
that
initially going to
number
And then I
is
couldn't
this
go back for
number
that.
right
It was
here.
just backwards.
Yeah.
It happened
All right,
backwards,
so
but
now,
it's the mean.
so
But
20, now we're
I'm
gonna
sorry.
it's
say
over now, so.
I mean, I saw it. It did happen.
112-pound person
It's very.
can carry this amount, and I'm gonna tell you, fill that in. Now, we are 95% confident. We are 95% confident that a 112-pound person can carry, and instead of having one answer, we are going to be 95%. That's 2 standard deviations from the mean. So if we said the standard deviation is 3, we're going to add 26.4 plus 2 3s. So what's that? 32.4?
I just realized we
On
keep
the
talking
upper
to
end.
Joel, but it's also
Why 2 of them?
Kevin.
Because
and,
we're
no, it's just Kevin.
95%. It's really not 2. What is it really? What's the Z
Like
stuff?
2.15 or something?
1.96?
Oh, sure.
Alright, I forget. But it's almost 2.
Wait, how did we get 32.4?
We added 2 standard deviations because that's about how many
6.
standard deviations are from the mean to get to 95%.
And you just told us the mean.
Right.
But
Well,
we
it
didn't find it.
came from our regression line from chapter 3. When we put in a 112-pound person, we got out a
Oh,
26.4, and we added 2 3s to it. And then what if we subtract 2 3s? We get what, 20.4?
Wait, so can I see that equation one more time? I think I deleted it.
Alright, check my math. If I subtract, yeah, 6. 26 minus 0.4 minus 6. Alright,
Where
so
do we get the confidence level? How do
we
we
just
get?
made it up.
Yeah, we're just like,
We picked it. This is how sure we want to be. So we could say 90 or anything. Alright, so this is where we're aiming. This is theory. So now I'm going to give you the real McCoy formula for doing this work. But this should give you an idea of what we're aiming toward. Alright. And again, you don't have to understand this theory. It should be at least presented to you. It will not decrease your ability to find the confidence interval. All right.
It's
Alright,
Patrick.
so
He
let's
like a
do-
flag.
It was fun about the movie.
Here, I'll give you the formula and then we'll do one. Alright, in order to do a confidence level, do you recall how we did it with X bar? So this is just in your thought clouds.
How we got?
I think it's level.
X bar and P hat. Let's start with P hat. We did plus or minus. Do you remember what
Square
followed
root,
it?
Z star.
Z star.
Beg
And now comes square root. Anyone recall what went in there?
P times 1 minus P.
Over N.
And that was with hats on. Alright?
What?
Alright, you don't need this. I'm just showing you what we did in the past. Do you remember what this was called?
We don't know.
Confidence.
Standard error.
Standard error.
Good job.
Now, can you remember how X bar differed?
The inside under the square root. And Z.
Oh,
it was
T.
T star.
T star, that's if you don't know the standard deviation for the whole population, but we never
That's right.
know
There
that.
are also
Anyone
N's.
recall what
And that's how you find the standard error of
That's
X.
so
So
bad.
it's the
Square root.
standard deviation over the square root of N, right?
Right.
Oh, is
Alright,
that the
standard
you're right.
deviation of X over the square root
That
of
was
N.
what you were
And
thinking
that
today.
is.
That's where I was
that's
headed.
error.
That's my brain.
Alright,
That's
so
what I thought you
that
were
was
doing.
the past.
That's
You'll
the
see
thought.
now that
Those
we're
are the
doing
cloud.
inference around slope, it'll be somewhat similar. So here is confidence interval for slope.
So we don't really need to, like, this theory that we talked about today is just on the back burner.
Yeah, yeah. You'll
No,
just
I'd
see
rather
that
you
it's
see
very
it.
similar. So we're going to do a confidence interval for beta, which is slope. And here's the formula, and we'll do one or get one started. So it's going to be,
What we just did, just like for this whole class, was that a confidence interval?
yes.
Okay, so now we're just doing it in a different one.
This
Well,
is
we're
just
actually
a
doing
equation.
it. That was just kind of
Theory.
theory, pie in the sky.
Back
This
burner
is-
theory.
This is the actual how we
This
would
is
put
the
it in
real
our
shiznit.
calculators.
Actually, I
and
really
do
want
it. Alright, so we start out with B.
Okay.
B is from our sample.
Yep.
It is the slope that we found on our sample. So that's the sample slope. B, and then we're going to go plus or minus, just like we did when we were doing P hat and X bar. We're going to go T star again. So that's chart what?
B.
Charty B.
B, chart B. And then it's going to be followed by the standard error of B. The standard error of B. So, are you surprised? It looks pretty much like what we did here,
Seb Bush.
except I don't have a formula for standard
Bush for
error of B. Let me show you what the
Seb is
standard
a
error
mess.
of B is.
Okay.
The standard error for B is S, and on the first day on the blank piece of paper, we went over what S was from chapter 3, over S of X, which is the standard deviation of the sample times the square root of N minus 1.
How do we know
So-
these numbers?
How do we know what?
How do we get all these numbers?
Standard deviation in our calculator, basically. However, I've never seen anyone be asked to calculate this by hand. It is almost always found by
So-
Minitab.
Minitab.
The sub is always found by Minitab.
What?
Mini tabs
The
have kind of
seven's
turned
always
against
found
us,
by
I feel
Minitab.
like, because they're hard
I'm
to
sorry.
read now.
The what is?
That
A standard error of B.
Yeah.
How to read
So
it.
that's
Like,
it.
that's
The what? The what? The
You're
what?
how dumb you think I am.
Alright, so,
It used
let's
to be
see
good,
what
like,
you can do.
you should just tell me the meaning.
The bell's gonna ring. Let's see what you can do with the helicopter experiment. And if you notice, all of the data you'll need for liner is already in front of you. You see that? They did a normal probability, they plotted the thing, they did the histogram, and then they did a mini-tab, and they did a regression plot. So, if you could, for homework, give this a try, even though we haven't done one. And go as far as you can go, and you're going to try to find a confidence interval that they asked for on the helicopter experiment.
Okay. 95%?
Yeah, 95%.
Okay, great.
Miss
She said she
Powell,
did your DHL.
are we gonna have more opportunities to have grades when we start reviewing for this not